one interferes with the recording or the mic, I cannot see all those things at the same time. I'm trying to record this to help people who are not here, all right? So let's behave and be mindful of others. So the first thing is you must change the capacitance and the inductance to their reactances. Now, up to yesterday, when I was doing evaluations, I saw that there are still a number of students who still have a problem with the very first material. So let me emphasize it here. Capacitance, C, and inductance are not the same as capacitive impedance or inductive impedance. They are related, but they are not the same. All right? You cannot write an equation and say Z is equals to R plus C or minus C plus L. This is completely wrong. So the first thing to note is that we are dealing with AC circuits. And when we are dealing with AC circuits, as far as this course is concerned, we're dealing with reactances and impedances and phasors. So the inductor here is 0.5 Henry. If you come down here, I hope you can see my arrow, right? The inductive reactance is given by omega times L. Omega is the radiant frequency. And the radiant frequency is given right here in this equation here, the source equation, right? Here. It's omega T. So your omega in this case is 1,500. So that's your angular frequency, all right? So when you want to find the inductive reactance, you have to use the frequency omega, which is 1,500. And therefore you see I come here, down here, I multiply 1,500 times 0.5, which gives me 750 ohms. Reactance is a pure number, right? I then write ZL, which is the impedance now of the capacitor. There must be a J here, right? So this is J750 or J0.75 if you want to express it in kilo ohms. So the same thing for the capacitor. The capacitive reactance is 1 over, right? Is 1 over omega C. Omega is 1,500. So we write here 1,500. And the capacitance is 1 times 10 to the minus 6. And if you work that one out, it gives you a capacitive reactance of 666.7 ohms or capacitive impedance of minus J 0.667 or minus J 666.7 ohms. So those are your two reactances. So you can now go back to your circuit, and here you can indicate this as J750 ohms. This you can indicate as minus J666.7. Come on. There you go again. It has unshared itself. I don't know what is happening. The program has gone out, so I have to bring it again. One not. Okay, I have to share it. Okay, I was here writing for the capacitor. The capacitor will be 666.7. It's minus J ohms. So now we have all the components in terms of impedances, right? We can now do KVL equations, right? So this is, but maybe before you do that, you can write your input voltage in phasor form. It's given as 15 cos 1500 T. You can express it like this. You only need to remember that your reference in this case, right, is cos omega T. Omega is 1500. That's your reference, all right? So this is my input voltage. So with that, I can now write my first KVL equation around I1. So this is the equation. 15 omega 0 is equals to the drop here, which is 75 times I1, and then times this impedance, which is minus J50, J66.7, the net current flowing in this direction, right? Flowing in that direction. Come on. Okay. The net current flowing in this direction here, whilst we are in this loop, is this impedance times I1 minus I2, because I2 is going up and then I1 is going down, which is this term here, I1 less I2. And then here you are just rearranging, put the I1s together and the I2, so you get that equation, 15 angle 0 is equals to that. And then in the second loop, there is no source. So one side is going to be 0, which is this, all right? These two components, the 0.5 Henry or J50 ohm inductor and the resistor are in series. So you can club those two together and simply write them as 100 plus J750. That's one impedance. So times I2, it gives you one voltage drop term, which is this term here. This is meant to be 750. This here, it's 750. J750 times I2 plus 100 times I2, which is the drop around this. And then when you come to the capacitor, when you're doing this loop, current I2 is going up and I1 is going down. So the net current in the direction of I2 is I2 minus I1. I2 minus I1 all together multiplied by the capacitive impedance. So that gives you that equation. You see? Then again you regroup, that is you collect the I1 and the I2 terms separately. The I1 term is only coming from this term here. This side you have I2, so this is negative, negative. You are going to have J66.7 times I1 plus 100, the real part, and then this is 750 positive. The I2 term, this is going to give you 666.7 negative. So you add those two, you get plus J83.3. So this is the second equation. And then I put the equations together right here. Right? The first equation is at the bottom. The last equation is at the top. At this point, you can pursue the solution method of your choice. You can either go the matrix way, which I have shown here, or you can solve these two equations simultaneously. You see, because this top one is equals to 0, you can use the top one to express in terms of I1 or I2. Then take that expression into the second equation. You only have a lot of complex, numbers to mess around with to get your final solution. Or if you put it in this form, which we have covered in class, then you can easily get the inverse to find I1, I2 will be equals to the inverse times 0, 15, right? Now, the inverse of this matrix here is obtained by changing the positions of these two. They are the same, so it will be J666.7, J666.7, and then you negate, in other words, you change the signs of these two, right? You put a negative ahead. So you can repeat this one. It will be minus in brackets 750 minus J666.7 in brackets, and then this one will be minus in brackets 100 plus J83.3, right? And then here you multiply, you divide by the inverse of the, you multiply by the inverse of the determinant. And the determinant in this case, you know that it's going to be this times that, which is J666.7 squared, because it's the same, minus these two multiplied. So it will be 750 minus J666.7 times 100 plus J83.3. You evaluate that and bring it here. So you do the rest of the maths. I will not do that part. That is left to you, all right? The memo has got the solutions complete, so you can also refer to that. Is there any question? Okay, let's go to, sorry?
You can carry on, say no questions.
Thank you. Let's go to question 2. All right. So question 2. You are given a network. Now observe the parameters. In this question, the circuit, I'll draw the circuit here. You are given a source. The source is specified as VM, which is 10 cos omega t. You are told omega is equals to 33.33 kilo radians per second. All right. This is a voltage source. And then the first arm has got an inductance 15 millihenry in series with 500 ohm resistor. So that's an impedance, right? So it is R plus J omega L. If you put this frequency is kilo, right? 33.33 kilo times 15 millihenry, you'll see that is going to be 500. So this one I can write right away and say it's That is the impedance. All right. And then on here, I've got a resistor. The resistor is 1.5K. So this is 1.5K. And then next to it, I've got a capacitor. The capacitor is 20 nanofarad, all right? So let me calculate here roughly. You see, when I'm doing this now, I don't really mind showing the work to calculate the capacitive reactance. But I can just write this is omega C is equals to 3.33 K times 1,000 because it's kilo, and then times 20 10 to the power nano, which is 9 negative. So this gives me, you can calculate that side, your side. So 3.33. Oh, my calculator is in a certain mode. I have to check how to take it out.
Negative 1,500.15.
Okay, thank you very much. But remember, I'm here calculating the product, so there's no negative yet, just to be consistent, so that I know you understand what you are doing. What is the number there? Come again. 1,000.
Negative J 1,500.15.
1,500. All right. This is not omega C. I think she calculated 1 over omega C, which means let's correct this one. It's like that, you see? And then she was saying minus J, which means she put minus J here. So it's minus J there, so that becomes minus J. That is correct now, all right? So I was calculating the admittance when I didn't write it as 1 over, because it's easy for me. So this, we go back to the circuit, is actually minus 1 J 1.5 kilo ohms. To that, we've got a current source, and then we can complete the circuit. The current source is 14. Notice that the voltage there is 10 volts peak. Now this one is 14.14 milliamp. It's always good to keep the units the same, not to confuse things, all right? So I'm going to leave it as 14.14 angle minus 45, right? It means because I've left this in milli, this is milliamp, it means all the calculations which I must do here, I must change my impedances to K, because I'll divide by 1.5. So it means whatever current I get will be milliamp. So I'll go back and express this one as 0.5, this one as 0.5. So all my impedances are now in terms of K. So this is K and so on, all right? And we are required to find that voltage. Let's call it VC. We are going to use node analysis. This is quite simple because all what we need to do is erase that. Okay, we just have to apply nodal analysis. First, we indicate our currents, all right? like that. Now, if you notice, we have really 3 branches. This is feeding into, we call this one I1. This is feeding into, we can call this one I2. This is feeding away, we can call this one I3. This is going away, we can call I4, right? So that is quite straightforward. So there is 2 inflows and 2 outflows, which means we can write a KCL at the node of concern and say that I1 plus I2, I1 plus I2, the 2 inflows, which means this current and that current, should give us I3 plus I4. So that should be I3 plus I4, you see? So that settles that. So the next thing is we just use Ohm's law. This current I1 is the voltage drop divided by the impedance. The voltage drop is going to be 10 angle 0, because that's the source, that's the voltage at this node here. So I1 is going to be 10 angle 0 minus VC, the voltage that we want, all divided by this impedance. Because this current here is milliamps, so I've taken out the, I will express this as 0.5 plus J 0.5. So that means that current is now in milliamps. Plus I2 is given, is this 1414 angle minus 45. So this one is 14.14 angle minus 45 degrees equals to. Now these 2 branches here, of course, are in parallel. They've got a common voltage VC, and of course the current in each branch, you simply use Ohm's law for each. I3 is simply VC divided by 1.5. So this is VC divided by 1.5 plus, this is going to be VC divided by minus J15. So here you have VC divided minus J15, right? So you can see that this equation is all you need to solve. The only problem is you need to remove the VC from this side and put it that side. So we'll do that. This side becomes 10 angle 0, and then divided by 0.5 plus J 0.5 plus 14 angle minus 45 equals to, I'm going to take this term now, this one, it's negative here, so it will add that side. And I'm going to factorize to take out the VC right away. This time I'm going to have 1 over 0.5 plus J 0.5, and then plus 1 over 1.5 from this term, and then this one will give me minus 1 over J 1.5 in brackets VC. So my VC will simply be finally this left-hand side divided by that right-hand side. As simple as that. I just want to rub that. Okay. So your VC is simply going to be 10 angle 0 divided by 0.5 plus J 0.5 plus 14.14 minus 45 degrees all divided by this term here, which is 1 over 0.5 plus j 0.5 plus 1 over 1.5 minus 1 over j 1.5. So you carry out that division. That is what gives you the value of VC, right? So again, I'll leave you to do that part. There are some students who don't like this, but unfortunately, we have to do things that way. For you, have a part to play as well. All right? Is there any question there?
Yes, sir, there is a question.
Yeah, please go on.
Okay. Going there to go to the second, say. Yes, there. You see I1, then I3. Why is the middle part neglected there?
Okay. Now, okay, let me go to this here. It's a good question, but let's try to paint it this way. You see, this is a conductor, remember, right? You agree?
Yes, sir.
This is a conductor. So if I have a branch which starts from here and is going there, and another branch which starts from here and goes there, you see that? And I've got another branch which starts from here and goes there, right? Now,
Yes.
the distance from here to there, from here to there, may as well be 0 meters, but it can be any even 100 meters. You see that?
Yeah.
Now, this configuration here, electrically, you can also draw it like this. Isn't it?
Sure.
So this electrically is 1 point there. This conductor is 0 resistance. There is no potential difference across there. It's just a conductor. It's 1 point.
Okay.
Yeah.
Now I understand, sir. Thanks.
Okay.
Yeah. Because say
Mm-hmm.
my challenge, seeing that branch there, hey, I was short circuiting everything, like, hey, this one short circuited.
Which
So
branch?
you see, seeing that common point there between
No, you see, you mustn't get confused with this here. This point here, this point,
yes.
these points here, it's one and the same points. That's why you see, I did not write a different voltage from there to there. I said it's VC.
Okay.
Yeah. This is like, you know, in the laboratory, right? In the lab, you were connecting at a point. Suppose this is a resistor, right? You would
Yes.
bring another wire and put the plug here. You would bring another wire and put the plug there. It's 1 point. You have 1 voltage at that point. This is exactly the same as this here, what you are seeing there, right?
Okay.
Electrically, this is 1 point. If I were to connect this point here, like in the lab, I'm asking you now, how many wires would be coming to that point?
It's one, say.
You got it wrong.
To which point, say? To
This point here, the one that you are confused with. This point, you can't see my arrow circulating around there.
I see, sir.
Yeah. How many wires would come to that point?
1, 2, 3, 4.
Yes, there will be 4 wires.
4 wires, yes.
Yeah. 1 for this, 2 this one, 3 that one, 4 that one.
4.
So where is this one?
Okay, okay.
You get it?
Yes, I get it, sir.
It's a common point. So there's only one voltage there, all right?
Yes.
Any question? All right, let's go to number 3. Number 3 is the question which a lot of you avoided, all right? Number 3 was avoided by all, if not most of the students, if not all. So let's try to pay attention. Now, before we answer this question, please make note that when we are talking about AC systems, there is this relationship that we spoke about in the lectures, all right? Sorry. Come on, it's doing its own thing here. P plus or minus JQ. You mustn't forget this. This is fundamental, right? We told you in the lecture that this here is called apparent power and is measured in units of volt ampere. This here P is the real power which is given in watts. This here is reactive power which is measured in units of volt ampere reactive. These 3 quantities here form a triangle. We called it the power triangle. This angle here is theta. The bottom side is P, the real power. The opposite side is Q, and the hypotenuse is S. All that you know about Pythagoras as it relates to right angle triangle is applicable. All right? Please note that P is a pure number. It's given without any angle. A lot of students in the test and in the evaluation, when you ask them to calculate P, they will give you a number and then an angle for P. That is completely wrong. P is real power. It does not come with any angle whatsoever. The angle is meaningless as it relates to P. Q is reactive power, right? It is a complex quantity. This is what you can give an angle, and the angle is 90 degrees. In other words, if it's inductive, it will be, say, J. If it's inductive, it will be J. Oh, where's my pen now? It will be J 800, whatever, volt ampere reactive. If you write it as 800 volt ampere reactive, to people who are dealing with a power, they will know that there's a J here. They don't have to be reminded because they see this R. You see, they know that strictly if you are going to do the maths, that R means there's a J. So you can write it without a J, but you indicate volt ampere reactive. You see, sometimes even if you write Q is equals to 800 volt ampere, if it says Q, then you know maybe that person just made a mistake. He omitted R because this is volt ampere reactive. But that reactive part will be sounded out because you are using Q. That is the convention. So P is real. and Q is imaginary. That makes S, which is a combination of these two, to be a complex quantity, S. Now, power is used as it happens. If you have got components in series, you have components in parallel, there is no formula which tells you that if you have got components in parallel, this is misbehaving. If you have got components in series, in parallel, say this is Z1 and Z2. If Z1 is using S1 apparent power and Z2 is using S2, the fact that they are in parallel, there is nothing that tells you that because they are in parallel, you use the formula as combining parallel impedances. There is nothing like that. Power, you simply add. It's add. Even if they were in series like this, right? Those two components, and this one consuming S1, this one consuming power, you still add. It's S1 plus S2, right? So there's nothing to say that, oh, because they are in series now, you add, or because they are in parallel, you use the parallel formula for adding power. No, there's nothing like that. Power is power. You add it. The only thing you have to take care of is the correct representation of the apparent power, if it's inductive, if it's capacitive, if it's real, you have got to express it correctly. So having said that, let's see what we are trying to say. So a factory consists of 110 kilowatt mechanical power output at an efficiency of, right, and a power factor. So now, if you are talking about a factory, right, it doesn't have to be a factory. To say it's a factory is just meant to throw you off guard a little bit, to test your analysis skill, right? But here is the thing. If you look at Mangosuthu, or let's not talk about Mangosuthu, let's talk about your home, right? In your home, if this is the home, outside there will be a meter box, and you will have a line there, Eskom line or Tequini line, bringing power to your house. So if you look inside here, there is a main switch where the power is coming from, the Tequini 220 volts. And then from that main switch, you have a series of switches at your distribution panel, where you take your power, right? So here you've got a bus bar. If you check inside the panel, that box where the electricity comes to, all these points here connect to a particular bus bar. And that bus bar is now connected to this main incomer. So this is your main. If this is 220 volts, everywhere here is 220 volts. And then the switch here might be going to lights. This one must be going to washing machine. This one might be going to geyser. In other words, all these things are in parallel. So in your house, you'll have a load like this, right? This is one load. Let's call it now load 1. And then you'll have another load. Let's call it load 2. Then you'll have another load. Load 3. So these are your 3 loads that are connected. That's all what we are saying, because they all come from the same source. every load is supplied at the same voltage. So that's what we are saying here. Instead of saying a house, you just put a word factory, but you know, it's one and the same thing. So the power comes in like that. What I did not do is put a source here. The source is known as 220 volts, all right? So that's just a picture. Let's take out this chairs here. Right, so this is our load. So in this instance now, what we are saying is load 1 is 100 kilowatts at an efficiency of 0.75 and a power factor of 0.75 again.
Load number 1 is 110, sir.
Okay, thank you. It's 110. All right. Now you see, we are receiving 110 kilowatts, but we are losing 25% because the efficiency is 75. What we are getting as output, the question says output is 110, but it's coming at an efficiency of, which means the input here from the supply side, let's call it S1 now, or P1, is going to be 110 divided by the efficiency 0.5, which is equals to 110 divided by 0.5.
147.
Okay, that's 147. I won't write kilo, right? You know we are talking about kilowatts, right? So it's 147 kilowatts. This is P. So which means the angle theta 1 is arc cosine, right? Arc cosine 0.75 is 44.4. This is 44.4 degrees, right? Now, this is P. And you know this is a power factor. You can go back to the power triangle if you want. Let me stay with the power triangle so that, you know, we're all clear. But you don't need, actually, you can do this in your head without drawing. I'm just drawing. So this is theta 1, and this is 147, right? If we know this, then we know everything, you see? Because we have got this and that side, we can calculate this side and that side using trigonometry. So 147 divided by S. 147 divided by S. Remember, S is this side. Will give us cos 47, which is 0.75. In other words, S is equals to 1747 divided by 0.75. So 147 divided by 0.75, it gives us 196. So S, sorry?
If you say shift cos 0.75, it's 41.4, not 44.
Oh, okay. All right. It's a correction. This number here is saying it's 41. And this one here. Thank you for participating. This one. Right. So it gives us 196, but remember there should be an angle because now this is apparent power. That angle is this one, it's 41 degrees. You see? So that is the apparent power from the first load. So we now have S1. And we go on and do the same for S2. S2 is 80 kilowatts mechanical power output. So the second one, P2, is 80K at 80% efficiency. And power factor 0.8 power factor leading. All right. So again, the real power input in this case, because this is what is coming out at an efficiency of that, will be 80 kilowatts divided by 0.8. So that will give us 100.
Exactly.
Sorry? This is 100 kilowatts. So again, we can do the same thing now. We know that if we want S2, we simply divide this 100 by 0.8, right? The power factor. So your 82 is equals to 100 divided by, it's 125. And then what is the angle? What is the angle? I'm doing
36.9.
Come again.
36.9.
I wanted you to say it correctly. It's minus 36.9. Remember, this is a leading power factor now, right? This one is positive because it was lagging. This is leading, right? So anyway, the next thing is S3, which is said to be a heating load. So S3, which is that one, is equals to 50 kilowatts at an efficiency of 100%, which means it's just 50, like this, plus J0. It's purely because the efficiency is 1, right? There is no power factor, and it's just like that, you see? So now we have got all the three apparent powers, 1, 2, 3, right? We can now start answering the question. To find the effective power of the source is going to supply all this power, S total. This is S1, this is S2, this is S3. So the total power is going to be S1 plus S2 plus S3. So you simply add S1, we found it's 196, angle 41.4, and S2 we said 125, angle minus 36.9, and then the last one is 50, because it's real. You add this one up, is going to give you a number and is going to give you an angle, right? That we can do very fast if somebody can help that side.
301.0.
Okay.
302 angle 10.
All right, let me check out this one. So this one you are saying is 300.
302 angle 10.41.
Okay. 300. See this thing here. 302 angle 10.
10.41 degrees.
The angle is positive.
Yes.
Okay, so it's positive, right, degrees. This is, remember, kilovolt ampere, right? So that is your total apparent power. So what is the effective power of the source? So now you can say A, the effective power factor of the source is cosine of this angle. So it's cos 10.4, which is
0.98.
0.98. Is it leading or lagging?
Leading.
It's lagging. All right. I'll come back to this to clarify the confusion. All right. I'll come back to that, why we say lagging, so that you know it once and for all. Or let me just explain it right here. There's no need to come back. Now, please remember, we said in the lectures, right? In the lectures, are you with me? I'm trying to explain in a way that you won't need to remember it to forget it again. In the lectures, this is the scenario. If I draw a phasor diagram like this, right? I'm going to draw the voltage phasor and the current phasor of a given load. Come on. I want to change the color of my pen. Okay. There you go. Now, suppose this is my voltage phasor, right? And then my current phasor would be here. So there is this angle here, right? Be with me, right? Is the current leading or lagging?
Lagging.
Okay, very good. So this current is lagging, right? We said to compute S, we write S as, you see that?
Yes.
Is the conjugate. So if this current is lagging, it means that angle is negative, isn't it?
Yes.
Oh,
Yes, sir.
yeah, I want to hear you, right? It means this current is negative, but if I compute the apparent power by taking the conjugate of the current, it means I'm going to change this angle now from negative to positive. You see that? So
Yes.
because the current was lagging, in other words, it had a negative angle, but when I compute the apparent power, I take the conjugate of the current, which changes the angle to positive. This is what you are seeing here. You see? If I ask you to calculate the current for this scenario here, you must know that the current is going to come up with an angle which is minus 10.4, because this shows the load is inductive. This is an inductive scenario. And if you do the power triangle, it will be like this. The Q will be positive here, and the P is here, and your angle is there. That is inductive. If it's capacitive, it will be the other way around. The angle will be here. It means it's positive, it's leading. When you take the conjugate, it's going to become negative. So when you draw the power triangle, it will be like this. Your Q will be down here, negative, and this is your P, this is your S. You see that? So if you remember it like that, you can't get lost. Right, so let's go to B. B, find if this, what is the source current in both magnitude Now, straight away from what I was saying, the total, S total, is simply 600 angle 0, that's given, times the current conjugate. That's what I've been saying. So your current conjugate is simply going to be 302 angle plus 10.4 divided by 600 angle 0, which means it's going to be 302 divided by 600, which is about 0.5.
Yes.
Angle 10.4 kilo amps. Remember, this is kilo, right? Because the top one is kilo. So, but this is conjugate. So to get the conjugate out, you take the conjugate of both sides. So here, I'm now writing the current without the conjugate, but I must take the conjugate of this side. Taking the conjugate of this side means changing this sign to negative. You see? So that is your current now, this. What is energy consumed by the factory in 6 hours? Now here, you needed to remember all your physics, right? And most of us seems to have forgotten. In class, I got very correct answers, but as I said, most of you avoided answering this question. Now remember, S, you now have it, is 302 angle 10. Can you please give me S in rectangular form? Somebody give me S. We have it in polar form 302 angle 10, but give me in rectangular form. ST in rectangular form.
X is 297.
297 plus?
Plus 54.5 degrees.
It can't be 54.
No, it's not degrees. Yeah, but why is 54.5?
Sorry, are you asking a question or you are letting me know the answer?
No, I'm telling you, sir, what you wrote is right.
Okay, so this is kilovolt ampere. P is this quantity here. P total is 297 kilowatts. That is the total power being supplied, you see, by the factory. But remember, energy is equals to power times time. That is the known formula for energy. Power is energy per second. So energy is power times time. So if you are told this time should be in seconds, so it should be power times 6 hours, but 6 hours is 60 minutes, and 60 minutes is 60 seconds. So this is your total power, which means it's 297 10 to the 3 times 6 times 60 times 60. You can express this in any units you want, megajoules, kilojoules, or whatever the number is. If you want to express it in megajoules, then you can divide this by 1,000,000, and your answer is going to be in megajoules. That will be the energy consumed in 6 hours. All right? Please don't learn and forget. Learn and add. All right, we have about 45 minutes. So that is question number 3.
Sorry, sir, I have a question here.
Mm-hmm.
Would it be wrong if I expressed the power in terms of VI changing T?
Sorry, come again.
Would it be wrong if I have expressed the power, the energy in terms of V, which is the VRMS multiplied by the current multiplied by the time?
You see, all what you are telling me is you have to be careful now, because remember here we are talking about complex power. What you have just said now is not P. You see, the way you have said it now, it's not P what you have mentioned, because you said V times I. This actually is S, and correctly it should be like this.
Yeah.
If you want power, then you must say it's VI cos theta. That is what will give you P, and it will come back to this number here.
Oh, okay. No, I get it now. I get it now. Yeah, I get it. Okay, thank you so much.
Sure. All right, if no further questions, let's go to question number 4. Number 4. In question number 4, you are given a motor which is operating at a certain voltage. So let's draw the scenario. Always in these questions, in any technical subject, it is always a good thing to do that. You must draw the picture, the problem, express it in a technical drawing. So there is the motor. All right. The motor is an electric load. You can just consider it as a Z. It takes in electrical power and gives out mechanical power. So it's used to drive mechanical loads, right? So the motor is 20 kilowatts. It operates at a voltage. So the input is 240 volts and it's 50 hertz supply. And the power factor of the motor equals to 0.76. All right, so this is the scenario. You want to improve the power factor from 0.7 to 90%. That means you can say this is power factor 1. Power factor 2, you want it to be 0.9. 90% is 0.9. Now, I sort of swapped those questions around because some people normally will not answer using step-by-step method. They will use the formula, you see, to answer in one shot. So I was trying to just want to make this look a bit better. It's not looking nice, it's looking skewed. I'm trying to redraw it. Okay. Here is the motor. 240 volts and 50 hertz. Now, you know that if we are going to do power factor correction, we connect a capacitor in parallel with the motor. So that is the answer to part B. But what capacitance is part A? So again, you can go back to first principles. The case is given, your power triangle, you draw your power triangle, right? So the power triangle is like that. The first angle, which we call theta 1, is equals to arc cosine 0.76. Arc cosine 0.76. Somebody help me.
40.54 degrees.
Sorry?
40.54 degrees.
Okay, 40.5 degrees. And then P is 20 kilowatts. Let's stay with kilowatts, right? So can you help me with Q? Q1.
Q1 is 17 kilovar.
So Q1 divided by 20 is equals to tangent of 40.5. Therefore, what's happening now? I can see it. Okay, we're coming to a close just now. So that is, then you can calculate Q1 from there is 20 times 40.5. What is the number?
17 kVAR.
Okay, it's 17 kilovolt ampere reactive. That is Q1. But you want to improve the power factor. Improving the power factor means reducing the angle by which the current lags the voltage. And you want to take the power factor to 0.9. Therefore, theta 2 is cos minus 1, 0.9, which is
25.84 degrees.
25.8 degrees, right? The others who are not contributing, you are very welcome to also contribute, right? So let it not be here only. What's your name, Sisi?
Nolutando.
Nolutando. Thank you, but I'm saying to others. You see, this angle here is what we want to be 25.8 degrees. This is theta 2 equals to that. Now, this is Q2, that distance. Q2, what is Q2? It's going to be 20 because this orange line from that point to that point and the P, they also form a right angle triangle. So this will be 20 tan 25.8 degrees, which is going to be equals to
9685 VAR.
968.
6.
I'll just call it 9.7. All right, this is kilovolt ampere reactive. That is, you want Q2 to be. So to get a power factor of 0.9, Q2 must be 9.7 P must be 20 still. Now, it means when you compare P1 and P2, it means you have taken out this distance here. That is what we call delta Q, the change in the reactance, the reactive power. Initially, it was 17. Now it's 9.7. So you must have added 9.7 minus 17, which is equals to
7.3 kilo.
Please notice that it's 9.7 minus 17.
Minus 7.3.
It's minus 7.3 kilovolt ampere reactive. Remember, a capacitor issues or gives out negative reactive power. All right? So this is the capacitance contribution. If you put a capacitor in parallel with the motor, it's going to generate or to contribute minus 7.3. So you add minus 7.3 to 17, the result will be 9.7. And that's exactly what you want. It will give you a power factor of 0.9. So now we know the contribution of the capacitor. So now we can say, therefore, cap must contribute minus 7.3 K. That is omega C B C squared should be equal to 7.3 times 10 to the 3 because this is K, right? But B, we know it. It's 200. It's given because the capacitor is connected in series, in parallel, sorry. And we also know W. And therefore, we can write C is equals to 7.3, 10 to the 3, or over 2 pi times 50, then times 240 squared. You calculate that answer, you can express it in microfarad or whatever the units, right? So that is where we are. There are some students who would like to use the one-stop formula and say delta Q is equal to P in brackets tan theta 1 minus tan theta 2. And then here they will say this is equals to omega C VC squared. And then they will move and write C is equals to P over omega VC squared tan theta 1 minus tan theta 2. This is what we have done exactly, only that we have done it in steps, right? So that is how
Excuse
you,
me.
yes.
Can I share the way I've done this problem? When
Yes,
you said you're
yes.
looking for a capacitor, I just said that Q we find the new Q, which is negative 7.4. I just say that QC is equal to X. I just said XC is equal to V squared over QC. Then I substitute. Then QC is the one that I get negative 7.3.
Sorry. You said what? V what is equals to what?
I said it's QC, the one that we get negative 7.3 kilo. I just said it's equal to XC.
No.
You get what I mean?
No, that is wrong.
Okay.
Remember, what we are getting is kilovars reactive. This 7.3 is kilovars reactive. So you cannot just equate it to the capacitance. It is capacitive reactive power. So capacitive reactive power, you calculate it by the voltage across the capacitor squared over the capacitive impedance. You see? Capacitive impedance is a V squared capacitive voltage over 1 over omega C. This is capacity, and this is what gives you omega C VC squared. You see? Then you form the division after, the same way I've done.
Okay, sir, thank you.
You need to compare like with like. Okay?
Sir,
Mm-hmm.
would you please re-explain what you've just said about getting UC?
Let me, you want me to explain here, this, or what I did here earlier on?
No, when it comes to getting UC, sir,
Okay.
there from omega C VC square.
Okay. You see, up to now, if you go back to this, I know what you have asked. This power triangle allows us to find the amount of reactive power we need to inject into the network to bring down the power factor angle, or in other words, to improve the power factor to a higher value. So in this question, you did not ask about how we are getting 7.3. You said how to get the capacitance from this figure. This equation here tells us that the capacitive reactance should be such that it contributes minus 7.3 kilovolt ampere reactive. So in other words, the power from the capacitor right, must be such that it contributes minus 7.3 kilovolt ampere reactive. That is the Q from the capacitor, the one that we are going to connect in parallel. Are you with me? Now we know that power in a capacitor, power in a resistor is V squared over R. Power in a capacitor is V capacitive voltage squared over capacitive impedance. Right? Just like here.
Yes, sir.
But capacitive impedance is minus 1, right? J over omega C. This is capacitive impedance. Are you with me?
Yes, sir.
This minus J, we understand that. You see, this is just saying it's reactive. And this negative is manifest there. You see? So if you take the magnitude part of this and the magnitude part of that, what we are saying is VC squared over 1 over omega C, which is the magnitude part of this, is equals to 7.3. That's all. So after this, you are simply solving an equation. At the denominator, you have got inverse of omega, product of C and omega. So you can write this as omega C, this squared equals to 7.3. Remember, this is K, all right?
Yeah.
And then from there, you are simply dividing because you want C. So you must take this factor and that factor and put it on the other side. And therefore, you're going to have C equals to 7.3 times 10 to the 3, all divided by omega times VC squared. Oh,
Oh yes, now I see.
right. All right, let's continue to the last now. We are in the last leg. The last leg is very easy. Question 5. Perfect. Now, question number 5. Draw a circuit showing a balanced three-phase delta star connected source. All right. You are going to draw a star connected source. The source is star connected, so we can start drawing it. So this is source. And supplies a delta connected load. So on the other side, you've got a delta connected load. Or you don't have to draw it like that. You can do it. That star, that circle. And then we can draw the impedances. I lost my point. You'll correct it. And then here, all right. So you label it. This is A, this is B, this is C. This is A, this is B, this is C. So we connect up our load. Like that. And now we have to connect the source to the load. A goes to A, B goes to B, C goes to C. All right? So this is delta load. This is star source. Further in the diagram, you have to show the following. Where to measure the phase voltage on the load side. The phase voltage is here. You measure it between any of these two. So VAB phase voltage. You see, you have to show that. You can measure it. You can show it between C and B. You can show it between C and A. That's all. To measure the line-to-line voltage on the supply side, you can show any two phases. Here you can measure the line-to-line. So you'd write here VAB, line to line. It's on the source side. Where to measure the phase current on the source side. This is the phase current, I, right? So you write phase current on the source side. Show where the star or neutral point, the star or neutral point is there, N. star or neutral point. That's all. And you get your 10 marks like that.
Sir,
So
after labeling my line as VAB, is it necessary to write line to line?
no, I have written it because I want to demonstrate that I fully understand.
Oh,
I'm just communicating to the person who is assessing. Because if you don't write it, well, I'll have to assume that, you know, because I wouldn't know which one is relating to which question. I'll have to think about it. I would know, but I'm trying to get in your mind.
Sir, I was still going to have this section on this upcoming test.
Sorry, come again?
I was still going to have this section on this upcoming test.
It will be even more than this.
Ish.
This is very important. Yeah.
sir. Sir,
Mm-hmm.
if it will be going to, it is going to be more than this. Should it over, it will be calculations.
That is true.
Oh,
This is very important. You must get it. You see now, some of our friends are really not following on what we are trying to communicate. I don't know where we lost each other. Because I told you in the first instance that you have somebody who has gone through age 2 and he writes impedance like this. And then he puts 100 plus the value of 100 millihenry minus 1 times 10 to the power minus 6. And he's trying to find an answer and give this as a value of impedance. What do you think about that? This person is left behind. It means they never attended the first lectures. They did not follow on the material in the handout on Blackboard. Somewhere, somehow, there was a disconnect. You see, that's why they end up doing this thing. But in this course, this is always the first thing you see you do. When you go and say, okay, in a resistor, voltage and current are in phase. In an inductor, in a capacitor, the current leads the voltage by 90 degrees. In an inductor, you know, this and the other. This one, the impedance is omega L, J. That one is this J, whatever, omega C, and this one stays R. And then you talk about the combination of parallel series and whatnot. So these things are very, very basic. To come at the end of the course when you are being assessed and you are still showing it like that, is a very bad reflection of what I've tried to teach, you see. So that's why it's important to test you on the fundamentals. And this section here, most of you, when we taught it to all the groups, you were not coming to class. But I said there are videos on Blackboard and even these recordings. I would say go to Blackboard because the videos on Blackboard are not disturbed. You don't get people, you know, interrupting me, interjecting me. I was just recording myself. So you can easily follow that.
Sorry, sir.
Mm-hmm.
Where exactly do we find these videos on Blackboard?
They are there. Have you gone to Blackboard?
Yes, I did.
Let's do the tutorial. At the end, you know, I will come back to you.
Okay.
We have gone through the questions, friends, and it's 1.5 hours. Is there anything else you want to ask here?
Yes, not a related question, but I'm one of the students whose marks are not appearing on the mark sheet.
Which one is that?
No, the last test.
You
The
mean
one that,
two?
yeah, test one.
Why is that?
I'm not sure.
I've given out the scripts, eh?
Yes, I've got my own script with me right now, but my marks are not appearing on the mark sheet.
Bring it next week.
Okay, no problem. Thank you.
It's fine. Bring it next week. Or if you want, you can scan all the pages and send me an email.
Okay, I think that would be better also.
Mm-hmm. Is there anything else?
Sir,
Mm-hmm.
sir, can you do just one problem of three-phase calculations?
Okay. Let me see if I can share a question with you so that you can take a picture and we'll go through that question. So give me a little bit of time. Right, you can take a short break, 5 minutes, whilst I look for a question. And I'll put that, but it's fine. Carry on. Okay. Let me share this one with you so you can write it down. What I'm sharing with you, again, it is on Blackboard. It's the slides on three-phase analysis. So take down this question here. You can take a picture or whatever. Are you with me?
Yes, sir.
Yeah, you can take a picture, you can write, and let me know when you're done. Okay, I'm sure you've taken a shot. So that is the problem. I'm going to unshare it. Are you done?
Yes.
Okay, I will unshare it so I can start the answer. Do this. Okay, this is the question. We will try to illustrate. Now, we may just do it to one example, but remember the principle applies across, right? You must stay with the principle. It will apply across. So let's just review. Okay, here come on, all right. I want to check on this one. All right. Now here the source is star and the load is star. All right. Now The network that we have here is called a balanced network. And for H2, you are not going to deal with any other scenario but balanced case. By balanced, what we mean is, if you look on the load side, the impedance in all the three phases are the same. So it's 24J19, 24J19, even for the other phase which is not shown, is the same. If you look on the lines, you'll see that the line has got its own impedance, the blue one, which is 0.6 plus 0.7. And then you come to the source. In each phase, the source has got its own internal impedance, which is 0.4 plus J3. And it is the same in every other phase. The values are only shown in one phase. The line to line, the phase voltage, the currents happening in all these three phases are the same. And because that is the situation, the source, the load are described as being balanced. So we are going to deal with balanced networks. Now, if you are going to deal with a balanced, come on. All right. No. It's not sharing what I want. No, sorry. Something has happened. I don't know why. Go away. I'm looking for my one note. It has disappeared. Okay, there we go. I'll try again. So yeah, I was just explaining that this network is balanced. So when you are dealing with balanced networks, you can zero in on one phase for your analysis. You just consider what is happening in one phase. Because it is balanced, the same thing will be happening in all the other two phases with the correction for the correct phase angle only. Now, we normally use what we call a one-phase equivalent circuit when the network is balanced like this. Now here, you are asked to calculate the line currents and voltage for the star-star system. And then you are given some parameters. You are told VAN is that, BN is that, right? So this is on the source side. Now, if you look at the green, phase A, we can redraw this, right, as one phase. We are going to look at what is happening in one phase. Right? So in phase AN, here, this source, we'll see that there is an internal impedance. The internal impedance is 0.4 plus J 0.3. Then there is a line impedance. So you see the line stops, I mean the machine stops there, the source, and then we start with a line which has got an equivalent impedance of 0.6 plus J 0.7. And then we continue, we stop with the line, and then we now have a load on the other side, which has got an impedance of 24 plus J19, right? This is one phase. You can close the circuit via the neutral, this line, right? So now the voltage on the source side, it's given VAN, it's 120 angle 30. So right here, this voltage here is given, it's 120 angle 30, right? So VAN is given. Now, you remember that the three-phase voltages are 120 degrees apart. This angle to that is 120. This angle to this is 120, right? So the only thing different here is that our AN is starting with a 30 degrees, not 0. So that is just a displacement. You don't have to worry about that. Just take it as it is. When we write whatever the voltage VAN is equal to V peak angle 0, it's just that we are starting at 0. But there is nothing which says we can't start at any other angle. And this is the situation here. We are starting at 30 degrees. But you must know that the voltages between them, there is 120 degrees, right? You can show that by drawing the phasor diagram or checking these displacements here. That's 120. So what is important is to identify the correct source voltage on the single phase equivalent. So here, the source voltage that will appear there is doubtless this, which I wrote there. And of course, that is what is going to drive this current in there, right? Now, you may wonder and say, okay, 120, what about this, right? There is not much lost. Even if you were going to assume, you can argue out. You can assume that this 120 is right here. Sorry. Oh, goodness. It's rubbing. You could have taken your internal impedance and wrote it there, 0.4 plus J 0.3, and said this I'm trying to rub this thing here. This impedance connects to that source. You see, so this is your 0.3. So your voltage will be here. Remember, it's the same voltage which is driving the current through the internal impedance, which you can model like this, and then through the line impedance, and then eventually through the load. You see that? So you can argue like that, because the 120, if you are going to place it here, you are saying the 120 is exactly the voltage which is appearing at the terminals of the generator. This is a generator, three-phase generator, right? Or you could argue and say, the actual 120 is the one which is right here. In which case, the voltage that is going to appear here will be a little lower than 120. If you assume the 120 is here, then the voltage that is going to appear there is going to be a little bit more because of the drop here. So there are those subtle differences. But anyway, let's ignore that and let's assume that this is the driving voltage, which is driving the current in the whole three series components. Let me take away that. So once you've reduced it to this, every other question which you now need to analyze is just a repetition of what we have done. Like now, they are saying find the line current. For this, if I want line current, I just have to add those three series impedances and divide by the voltage. That line current, Z total, the total impedance will be 0.4 for the source, J 0.3, plus the line 0.6 plus J 0.7, plus the impedance itself, which is 24 plus J 19. So you add that. This gives you 1.4 plus 0.61, so the total will be 25.3 plus that will be 1 again, so the total will be plus J20. So this is the total impedance. And then the line current, the current that is now flowing here is the same current. This is going to be flowing there. And this is IA. So this current here is line current IA. So IA is going to be the voltage 120 angle 30 divided by 25 plus J20. So can you give me that number?
$3.75 at angle negative 38.66.
All right, so this is IA. If I want IB, I can just write it right away from here. I know it will be the same magnitude because the network is balanced, but the current will be a further 120 degrees away from this. So it will be minus 38.7 degrees minus 120 degrees. You add those two. That gives you minus 158, right? So the net angle will be minus 158.7 degrees. For IC, it will be the same magnitude, 3.5 minus 38.7, but it will be minus 240 degrees from that. So you add again, that will give you minus 278.7 degrees. Those are the three currents which you have to, to write. So you basically calculated the three line currents, IA, IB, IC, right? Now you are asked to calculate the line voltages. Well, here it is not specific, right? Line voltage, it just said line voltages. There are two sets of line voltages which you can calculate, if not more, depending on where you are, right? Like now, I assumed at that point here that this voltage 120 is appearing at this point here. You see? Let me choose a different color. I've assumed that it's appearing here at this point. If I want to calculate the line voltage at that point, which will be on the load side. Then I can lump these two together. My circuit will be like this now. 120 angle 30 volts. And then this is my source and line put together, which will be 1 plus J. And then my load standing by itself here, which will be 24 plus J19. And then I connect, right? So if I want to find the voltage on the load side, this is voltage AN dash, but on the load side, I can just use voltage division because this voltage here I know, I've assumed. So I can write VAN dash to mean on the load side. You use voltage division. If this is Z load, and let me just say this is series impedance, we know where it is coming from, then it will be Z load over Z load plus Z series times 120 angle 30, voltage division. Then you enter the numbers. So 24 plus J19 all over 25 plus J20 times 120 angle 30 degrees. Can somebody calculate that number there? You divide these two and then multiply by 120. The same things that you did in Eng 1, only that now you are doing it with complex analysis, nothing different.
Okay. It's 114. It's 114.
Oh, okay, just hold on. Yes, 114.
0.73. Angle positive 29.71.
Yeah, you see, this is the voltage which will actually be seen at the load. So the load will not see 120 volts, it will see 114. There's a lot of loss of voltage due to this impedance, which is representing the impedance of the line and the internal impedance of the source. So they take about 5 volts out of there, right? Now, if you want the other voltages, again, you can write it by inspection B, and it will be this same voltage, 114.7, and then it must be 120 degrees behind this. So it will be 29.9.7 minus 120. 29.7 minus 120. So it will be minus 90.3 volts. Cn, it will be 114.7 angle. This one, 29.7 minus 240. So it will be minus 210.3 volts. You see, those are the voltages that you see, right? So in this case, those are the 3 voltages that you would calculate depending on how the person is configured. If I asked you to calculate the power used in the load. You can calculate the power used, let's just say find total power, total apparent power in the load. You could say the total apparent power in phase A is simply the voltage in phase A times the current conjugate, right? So this we now know it is given here. The voltage in the load is 114. So that one will be 114.7 angle 29.7 times the current. We have calculated it. There we find it 375. So it was 3.75 angle. Remember here it is minus 38.7, but we are taking the conjugate. This is conjugate, so we write 38.7. So when we calculate this, we are going to get 114.7 angle 0.7 times 3.75, 38.7. So it gives you 430, and the angle is 0, right? Is that right? No, can't be right. 114.7. 68.4, right? This is volt ampere, but this is only in one phase. So the total would be 3 times SA, because this is happening in all the phases. So the total in all the phases is going to be times 3, which is 1290. The angle doesn't change, it will be 68.4 volt ampere. That is the total power used, you see. I've just calculated the normal way for the single phase equivalent and then multiplied by 3 to get the total. If I want the power factor, I can just say, is equals to cos 68.4 degrees, and whatever that number is, that's your power factor. So that is how you solve these three-phase equations. You have to find the correct voltage, and then you have to find the correct current, right? I won't solve this one, but just to help you with answering whatever might be presented before you, I'll just illustrate. There is no numbers to this, it's just, and I'll close after this, right? If you have got a star source on one side, but instead of a star load, suppose you have a delta load, right? And suppose here there is no line impedance. I just give it as it is to make it simple. So this is A, and then this is B, so it will connect here. And then this is C, it will connect there, like this. So I told you that this side here, let's say there's 240 volts. For three phase, if I don't say anything, I just say 240. you must know that this voltage is a line-to-line. Three-phase system, we normally specify the voltage as a line-to-line. So, but if I say VAN is equals to 240, then I'm telling you this is phase voltage. So you can't just assume, you see, I've told you. So just like in the previous question, it shows here, it's given as VAN. So that's a phase voltage. But if I just told you the supply is whatever the number and didn't say anything, you must assume that the voltage is a line-to-line voltage. You see. So, but in South Africa, the normal level of the line-to-line voltage is 380. Is 380 volts or sometimes 400 volts. So when you see the voltage is like that, it's a three-phase source. And then they just give you the voltage as 380 or 400. You should know that it's a line-to-line voltage. If he's talking about South Africa and then it's a three-phase source and I give you 220, you know that you are given a phase voltage, right? If we just give and no talking general, you are safe to assume it's line to line. So now for a situation like this, if I specify this impedance and say it is 19 plus J20 and is balanced, and I asked you to do the calculation to find the line currents and the phase currents, you would proceed exactly the same way as we have done, but you need to be careful as to what, because your calculation is going to start here because that's where you have the impedance. So you would draw it like this, right? But if this is point A and this is point B, then you would see you have got A, B. Obviously, when you run this point from the load back to the source, you'll see that, come on, okay. You'll see, if I run this, you'll see that you are at this point. I wanted to change the color. You are here. If you run, that's for A. If you run for B, back to the source, you'll see you are here. So the voltage that you are actually talking about, which is across this load, is the voltage between A and B, which is VAB. So it's the line-to-line voltage. Then you go back, okay, this is the source. What voltage is given? 380. It means there is a line-to-line source. So you'd say this is 380 volts. You see? So now you see that even as much as we have drawn a single phase equivalent, we have correctly specified the voltage that is going to be applied across that. And when you calculate this current here, you are calculating the current flowing in that branch. You are not calculating this current. You see, it's that current. If you want this current, then you have to go back and know, okay, how is the line current in a delta related to the phase current? So you work backwards from there, you see. But this is your starting point. So if that is given, 19 plus J20, and this is specified maybe with an angle, you can obviously calculate that current, which will be IAB, the current in that phase. Use Ohm's law, YIB over ZAB. That gives you, and then every other current you can specify by phasing them by 120 degrees. And, you know, so the key is drawing the single phase equivalent correctly and specifying the correct voltage and the parameter which you are going to calculate in terms of the current, is it a line or phase current on the source? And then working backwards to find what is unknown. At that point, guys, I would call it quits. Thank you for listening. God bless you. We will have the test 2 makeup on, did we say 22nd? I think we did, which is a Wednesday. Right. I will confirm the venue. The lady maybe has taken a holiday, didn't respond, but on Monday, if I don't get a response, then we have to just make do with what we can. But going ahead, we will go ahead. So just keep your ears on the ground on Monday in terms of the venue. Bye.
Sir.
Okay.
Sir.
So,
I need to say the time will not change.
That's correct.
Oh, yeah. So say after the makeup test, we will be only left with the evaluation, simulation evaluation.
There will be a lot of things left. Don't go home and go into holiday overdrive. We still need you to come back. The semester hasn't finished. It will finish next year.
Oh, sir.
Yeah,
It was just that there will be no venues on January, sir.
No? What do you mean there will be no venues? There will be plenty of venues. All right. Guys,
so
the person who was asking about the videos, go to course activity and look for those videos. You will see them there. Course activity under 3-phase, introduction to 3-phase.
Oh, okay. All right. I'll go have a look. Thank you. All right.
Okay, bye. See you.
okay, bye, sir. Ciao,